On polynomial functions. So a polynomial function is a monomial or a sum of monomials. Okay, we write this in the form as follows here. Don't get super caught up in that notation. That just shows you that it is a sum of monomials with different coefficients and different exponents. Okay, and in some cases we have constants, which would be a of 0 here. Okay, so the main takeaway here is the exponents for a polynomial function have to be whole numbers, and the coefficients are all real numbers. Okay, so for the first three examples here, we are looking, are they polynomials or are they not? So for the first one here, we have f of x equals 3x squared plus 2x minus 1. So the two things we need to check: are our exponents whole numbers? We have an exponent of 2, exponent of 1, no exponent, so we're good in that category. And are our coefficients real numbers? We have a coefficient of 3, coefficient of 2, and in this case we just have 10. So yes, this first one checks all of the boxes. Okay, let's take a look at our second example here. We have f of x equals x to the 1/2 power minus 4ix minus 10. Okay, in this one, we have a couple of issues right away. So our exponents have to be whole numbers. In this one, we do have an exponent of 1/2. So already out of the gate, no, this is not a polynomial function. The reason for that being we have a fraction as an exponent. And the other thing that I notice, all of our coefficients have to be real numbers. In this case, we have a coefficient that is an imaginary number. So we also have an imaginary coefficient. Okay, so those are the two roadblocks from that one being a polynomial. Okay, the final one here, f of x equals all of that. Okay, first of all, are our exponents whole numbers? We have an exponent of 10, 7, 1, and then no exponent on the 1 there. So yes, those are all whole numbers. And then are our coefficients real numbers? We have -1. The square root of pi, yes, that's a real number. It's not imaginary. 4 and -1. So we're good to go in both of those categories. So yes, this is a polynomial. Okay, next section here. We are looking at degrees and leading coefficients. So degree is the highest exponent power of our variables. The degree indicates how many zeros for the polynomial. Remember, your zeros can be both real and imaginary. Your leading coefficient, we've already talked about this. It is the coefficient of the term with the highest exponent. Okay, so right here in example 2, this is already in standard form. That means that it goes from highest degree to lowest degree. Okay, the degree of this polynomial is just the highest exponent. So in this case, we have a degree of 4. Okay, the leading coefficient is just the coefficient on the term with the highest exponent. So our leading coefficient would be the leading coefficient would be the coefficient on our x to the 4th power. So our leading coefficient here is -1. And then finally, the degree indicates the number of zeros. So we have a 4th degree polynomial. That means that we will have 4 total zeros. All right, the next thing we're looking at is end behavior. End behavior is super important for those of you that are taking college algebra or pre-calc next school year. End behavior is the direction that the graph goes as x approaches -infinity. So as x approaches big negative numbers, or as x approaches positive infinity, which is just the numbers in the positive direction. So we have a nice chart here that shows all of the different scenarios, meaning our two different kinds of leading coefficients, and then the two types of degrees that we're working with. So in the first example here, we have 2x to the third power. Okay, and this would be a graph that would generally represent the scenario. So as x approaches positive infinity, okay, that would be this positive direction. Our function is heading up or down? Is it heading to positive infinity or negative infinity? Well, as we approach the right here, it is continuing upwards. So that would give us positive infinity. As we approach negative infinity, so the left direction, or the negative direction on our graph, our f of x, or our y value, is heading down, or it's heading the negative infinity direction. That would be the end behavior. So that is an odd degree positive leading coefficient. If it is even degree with a positive leading coefficient, as we head in the positive x direction, our function is heading up or in the positive infinity direction. And then for as x approaches negative infinity, when we head to the left, our graph is once again heading upwards to the positive infinity direction. I think of it as your x approaches tells you whether you're moving left or right. Your f of x indicates whether you're moving up or down. For a negative leading coefficient, as we approach positive infinity, so as we approach the right, our graph is heading down or in the negative infinity direction. As we are approaching negative infinity, our graph is heading upwards, so in the positive infinity direction. All right, now to even degree negative leading coefficient. As we approach the positive x value, our graph is heading downwards, so in the negative infinity direction. And as we are approaching negative infinity, our graph is still heading downwards, so in the negative infinity direction. We have a little bit here. If the degree is odd, then the tails go in opposite directions. If it's even, they head in the same direction. And you can see that from the chart that we just filled out. Okay, why don't you guys give these two on the right your best try based on whether, whether we have a positive or negative leading coefficient, and then whether we have an odd or even degree. So give those two a try. That's how we're going to start class. All right, on to the back page here. We're talking about relative maximum and relative minimum. So a relative maximum is the turning point of a function that is higher than the nearby points. So in this case, my relative maximum is going to be like the peak of my mountain. So this peak would represent the relative max. While the relative minimum is the turning point of a function that is lower than the nearby points. So this acts as like a valley. So this would be my minimum. The next thing here, we have real zeros. Real zeros are just any x-intercepts on our graph. So in this case, we have one x-intercept that they're showing us. Okay, so if we have one x-intercept, that means that we would have one real zero for this function that they are showing us here. Okay, so those are the next three things we're adding to this. So then these are the examples that we're going to be working with. Okay, let's try to knock out two of them, and we'll keep the other two for class. So the first thing here, we have to look. Do we have an odd or an even degree polynomial? So how we're going to figure that out is we're going to count the number of, we're going to look at the end behavior. So looking at your chart from the previous page, both of our tails are going in opposite direction, right? My left end is heading the negative direction, and my right end is heading the positive direction. So that tells me that we are going to have an odd degree polynomial. The next thing here is leading coefficient. Once again, this heads back to your chart. As I head the negative direction, we are moving in the negative direction as our f of x value. And as we're heading into the positive direction, our f of x value is heading positive. So this tells me that we have a positive leading coefficient. I found that from my chart. Okay, number of relative max and minimums. So we're going to count our peaks. I have one peak right here and another peak here. So this tells me we have two relative maximums. And conversely, we have two valleys, which would represent my relative minimums. And we have two of those as well. Okay, real zeros. From what I can tell, it looks like our graph touches the it looks like our graph touches the x-axis 2 times, but this one has a point or a maximum that falls directly on it. So my relative zeros, I would have one at x equals 1. So I can write 1, and this one would be a double root. And my other x-intercept would be at x equals 5. All right, now we need to write out our end behavior. So writing out our end behavior, the first thing you're going to write is what x direction are you talking about? So I'm going to start with as x approaches positive infinity. Then you are going to write what f of x approaches. So f of x would approach, so as I head the right direction, my y value is heading up. So positive infinity. Next, as x approaches negative infinity, f of x is going to approach. As I head to the left, my y value heads in the negative direction. So negative infinity. Okay, the last two things that I want you guys to write down are domain and range. In this case, my tails are heading opposite direction, and we are heading left and right. So my domain, my x value, is going to be all real numbers, or you could write negative infinity to infinity, doesn't matter. And my range, we're heading opposite directions, so that one will be also all real numbers, or negative infinity to infinity. All right, so I had planned to cover a couple more of these example problems, but I feel like this video is getting quite long. So we're going to call it there and save the rest of the problems for class. Okay, please bring any questions you guys have. I know this is a lot of new information, so come to class with lots of questions. Thanks for watching.